Breadth first traversal is also known as breadth first search. It is one of the fundamental algorithms in software engineering and computer science that is used to explore and analyze the structure of data, typically in graphs and trees. Let me explain it to you in simple terms. Imagine you have a collection of interconnected points, like cities on a map or web pages linked together. These interconnected points can be represented as a graph or a tree. You want to visit and analyze all of these points, but you want to do it in a systematic way. One such systematic way is breadth first search. The key thing about breadth first search is you start from a specific point, that is a starting node or root. For example, we can start from 1 in this particular graph. Then we explore all the neighbors. So the breadth first search or traversal says that explore your neighbors, explore the neighbors of the current node or current point, and then move on to the neighbors of neighbors. So for example, like if I start from 1, I would then traverse to 2 and 3, and once both 2 and 3 are done, then only I'll move on to neighbor's neighbor, that is 4 and 5 and 6 and 7. So 4 and 5 from are 2's neighbors, and 6 and 7 are 3's neighbors. Let's say we are at point 1. We start with point 1, which is our starting node or root node. We would mark this as visited. Let's say visited is red. Once we mark 1 as visited, we are also going to put that to a queue. Let's represent queue state in here like this. So initially the queue contains only 1. As a recap, queue is a first in first out data structure where any element that enters first in the queue is the first element that is processed or exits the queue. What happens next is we are going to process the queue. So we will take out 1 and we would mark 2 and 3 as visited, put it in the same queue. So the queue contains 2 and 3. After inserting 2 and 3, this is how the queue's state looks like. So 2 is in front and 3 is in rear. What we will do next is we will repeat the same step. We will remove the front element from the queue, that is 2, and process it, and then we are going to insert the neighbors of 2 in the queue, which is 4 and 5. But before inserting, we would also mark them as visited. So marking them as visited is the key point here, so that we don't traverse the node that we have already visited again. That helps us with that. After doing this, we would keep repeating the steps. We would extract out 3 from queue's front, process it. After processing 3, we would insert its neighbors, that is 7, because 7 is pointed from 3. So we are only considering the edges in which we point from the source and it goes to a certain destination. So 7 is neighbor of 3 and 3 is neighbor of 6, because this is a directed graph here. First we will mark 7 as visited, and then we are also going to insert it in queue. Next, we would pick the element again from queue. So we would pick 4, we would process 4, we would mark 11 as visited, and then we will insert 11 for further processing in queue. We will continue the same for 5, 7 and 11. So we will process 5, mark 10 as visited, insert 10 here. Next we will continue with 7. We will process 7, right? So when we process, we have to first remove the element from the queue. We process it, then we mark the neighbors as visited, that is 9 and 8 as visited, and then we insert them to queue. We continue the same. We remove 11, process it, mark the neighbor of 11, and in this case we don't see any neighbor, so we completely skip that. Yeah, we have 6 as neighbor of 10. We mark it as visited, and then we also insert it in queue. And we continue the same. We then process 9. We look, there is no neighbor of 9, so 9 is processed and removed from the queue. We continue with 8. We process 8. We look that there is no neighbor of 8, so we move on. Then we got 6. Now we can see that 3 is neighbor of 6 because 6 is pointing to 3. But since 3 is visited, we won't insert 3, and the queue will be empty in this case. So queue is empty here, and that will be the condition where we exit the traversal. Trees are the graphs without cycles. In this case, we can see we use directed edges to represent relation between two nodes, and there is no cycle in the tree. In such case, we can skip marking the nodes as visited. We can simply go ahead and process them, and before processing we first put the nodes in the queue and then remove the first element from the queue and process it in a similar fashion as graph. We start with 1, we would process it, then we will move on to 2 and 3, and then we will continue moving on to the next levels. So the way we are processing is level wise. This is the reason breadth first traversal is also known as level order traversal. And that is how breadth first traversal is done. BFS is helpful for tasks like finding the shortest path between 2 points, checking if a graph is connected, or exploring a tree or graph systematically. It ensures that we visit all the closest points first before moving on to the more distant points. To summarize, breadth first search or traversal is a technique that allows us to explore and analyze the interconnected data structures like graph or trees, starting from a specific point and working our way outward through the neighbors in next levels. It's often used in algorithms for tasks like searching, path finding, traversals, and so on. Perform breadth first traversal on this particular graph from a starting node, any starting node or root like 1, we have created a function called breadth first traversal that takes in graph and the starting node as input. We then create a queue, which is created by using Python list. We have also initialized a set to mark nodes as visited. We will start from the starting node. First, we will mark that starting node as visited and then we will put it in queue. Please note that we are putting it in queue in the back of the queue, and then when we pop, we will always pop from the front. So that way it will be first in, first out. After adding it to the queue, we will then loop through the queue and we will stop when the queue is empty. First step in the loop is popping the first element from the queue and tracking it as current node. We then process the current node. In this case, I'm simply printing it. We can do more complex processing here as well. Next, we will extract all the neighbors of this particular node, and then we will iterate through the neighbors of this particular current node. The neighbor is not yet visited. We will then mark that neighbor as visited and append it to the queue, similar to the starting node. And we will continue the same step again and again for each and every element that was inserted in queue. So if we start breadth first traversal from 1, this is how it's gonna look like. 1 2 3 4 5. If we start it by, let's say, 2, we will simply traverse 2 4 and 5. We will never reach 1 or 3 or 6, right? So 6 is the disconnected node here. If we start from 6, we can't reach anywhere, right? Yeah, so this looks good. To see if it is really correct, let's go back to the diagram. So 1 is connected to 2 and 1 is connected to 3. So that's why it has traversed 2 and 3 after 1. Next, 3 is connected to 5 and 2 is connected to 4. So 4 and then 5. 4 and 5. And then 6 is the disconnected node that I've added here, which is not shown in the diagram. What is the space and time complexity of this algorithm? So as we can see, we are initializing a set and a list. So set is initialized for visited and list is initialized for queue. As we have initialized them and we are inserting the elements in them, and the number of elements that can be inserted in these data structures is equivalent to the length of the graph. So the number of nodes in the graph is n, then the space complexity will be O of n. Because we can insert n elements, we'll have to keep track of n elements as visited. Time complexity of this code is O of n because we traverse each and every node only once. This can be misleading if we simply look at the nesting of the loops. The reason it is not considered in the time complexity is we have this particular condition in here that ignores the neighbors which were already visited. So that way, the complexity of the breadth first traversal in terms of space and time both are O of n. Thank you.